some point they stopped being excited because they said, oh, Bayesian deep learning doesn't work. And so I will try to explain what we did in the direction of making actually deep learning work, Bayesian deep learning work, which is mostly about looking for, thinking about what kind of good priors we can impose on these big models. And another thing I'm quite excited about is one of these projects on trying to use what we know about Bayesian statistics to actually understand what other models do in deep learning. So if you ever worked with GANs, or if you ever heard about GANs, generative adversarial networks, they look a bit mysterious. There is this two players game, and it seems to work. A few years ago, this was something people got really excited about before diffusion models took over. And so a friend of mine came to me and said, oh, I have a student working on GANs. Can you help him? You do all this work on trying to find good hyperparameters of models using Bayesian principles and so on. And so what we did was I sat down. I never worked with GANs before. I sat down and started to study them. And then eventually I came with an understanding of these models based on Bayesian deep learning, which allowed me to not only understand why these models work, but also to get a general formulation for GANs that is cast on Bayesian principles that is quite powerful, because now we, as people knowing Bayesian statistics, we know how to improve models by doing a posterior inference, understanding what regularization means in these cases, and so on. So we'll be talking about that pet project that turned into an absolute nightmare, because if you've ever worked with GANs, you know that training GANs is a huge pain. So I had to run a lot of models to convince everybody that this is a good idea. Okay, so let's get started. So first of all, I think one of the main motivations why Bayesian statistics is so powerful is that we can assist decision-making. And the decision-making is a critical step in lots of domains. And now with the wider and wider adoption of AI, of course, decisions happen everywhere. And this can be for the environment, for policymaking, for healthcare, making decisions about whether people should take treatments or not. In society, if you want to get a loan from the bank, now probably you're screened by some AI. If you apply for a job, most likely your CV is going to be screened by AI. So decision-making is becoming something, well, it's always been, but now in this process of automation, the question is whether we can do something principled and do this in a reasonable way. And so decision theory rests on two pillars, which are probabilistic reasoning and utility theory. So not only we need to be able to predict with what probability things will happen, okay, but also we need to assign a utility to possible outcomes. So if we know the cost of giving the wrong treatment to a person, or giving the right treatment, what is the utility of doing that, and or not giving the treatment to a person that needs treatment, all these outcomes have different costs or utility. Of course, this is not our job to assign these utilities. We need to rely on domain experts, medical doctors in this case, to tell us what kind of cost, monetary cost, unfortunately, because we translate mostly into that ultimately, we have to incur if we make the wrong decision. And so we need to know with what probability these things happen, and also we need to be able to assign a utility or cost to these outcomes so that we can optimize some form of expected utility. Okay. And so in this talk, of course, I will be focusing exclusively on probabilistic reasoning. Why? Because now we have models that handle very well data. We can introduce some physics if we are working with environmental problems where we have knowledge about the physics of certain processes. So we can integrate physics and data, and we can come up with amazing models that make predictions. And these days we've seen that with the rise of a lot of LLMs, this is becoming more and more something that is at the fingertips of everybody. And again, very tutorial style here. Consider these two examples, a regression problem. I generated this data from a true function in black here. I added some noise. So for any inputs x here, I have some labels y, which are continuous. And of course, for classification problem, this would be have some inputs, and labels here are just 0 and 1, triangles versus squares. Okay? And this is mostly to set the notation for throughout the presentation, that anything that we observe is going to be colored by orange. So in this case, x is observed, and labels y also are observed. And anything that we need to estimate, some sort of latent representation of our data, I denote in blue. Okay? So in this case, we're interested in estimating some form of function, f of x, from data. And I would argue that many problems in statistics and machine learning can be cast this way. So when people ask you, what do you do for a living? You can say, function estimation, right? And this is what I do mostly. And so let's think a little bit about neural networks, because these are the building blocks for a lot of things that we do in today in machine learning and statistics. So we take, when we do neural networks, essentially what we're doing is to compose functions, okay? So the power of these deep neural networks comes from the fact that we are taking unit functions that are simple, okay? So this type of function is taking any inputs, multiply some weights, and then apply some nonlinearity. But then we start composing these many times, okay? So this depth here, so when we start stacking all these layers, as we call them, we are essentially composing functions, okay? So this is the kind of representation we obtain. And this is really the power of deep learning, because now we have a machinery that takes simple units and by composing them can generate something which is extremely complex, okay? So function composition is really what gives this enormous flexibility to deep learning models. And of course, with this explosion in complexity also comes an explosion in complexity mathematically and tractability. So it's very difficult to study these models mathematically, precisely because we are doing function composition, and function composition is very difficult to study mathematically. Okay, so what most people do to optimize these models, they come up with some sort of loss function. Let's say that this is a regression problem. So we would set up a L2 regular loss function here. So we say that we want to minimize the discrepancy between the labels and what we can predict with our model. And then we add some regularization. And if we do that, then we obtain the picture that you see here. We obtain one function that goes through all the data here. And then if you change the loss in order to accommodate the fact that you have now labels which are discrete, you obtain something like that. And of course, based on what I was saying before, this is not maybe exactly what we would like. We would also like to know how uncertain we are about these functions, okay? Because maybe this is what my model obtains, but if you change slightly your regularization, if you change slightly your initialization of the model, maybe you obtain something else. And of course, I would not be able to argue that my function that I obtain here is better than the one you would obtain with your optimization, okay? And so there could be many different functions that fit this data equally well, I would say, or reasonably well. And so this is some of the stuff you find online. So there is this is a popular, ResNext is a popular convolutional neural network. And if you feed this type of image to this model, you will get that this is with 99.99% confidence, this is ping pong balls. And imagine now you have a system that has to handle this robotic agent that has to handle this for some whatever reason, not realizing that these are eggs, and this would be a disaster, right? You can find on this, I think it's a Instagram account or Twitter account, I forgot now. You can find a lot of these examples. This is the pineapple example, and so on, right? So you can find a few of these funny examples. And of course, again, in the spirit of what I was saying before, that uncertainty quantification is important for decision making, this type of overconfidence is really potentially a disaster for any decision making that will come after this. Okay, so we have a lot of examples also in the news. Think about the Tesla crash that happened a few years ago. I guess now they improved the vision model there, but all these things somehow may play a role in pushing us to be able to understand that we need to do a better job in quantifying this type of uncertainties. Okay, so how do we do it? How can we do it? So there's many ways to do it. I advocate for the Bayesian treatment of these models to be able to do this type of things. So if we think about the quadratic loss we had before, remember this yi minus f of xi squared. If we exponentiate and negate the loss, we obtain something that looks like a Gaussian here. And now the interpretation of trying to find the parameters that give us the minimum loss can be seen as the parameters that give us the maximum likelihood. Okay, so this is the connection between maximum likelihood and loss minimization. And again, you can see this either as something that we were trying to minimize a loss or something that tries to optimize a likelihood. And now this likelihood is the probability of observing the labels given the inputs and the parameters. So philosophically, it gets a slightly different meaning because now we want to find the parameters such that the observations that we have are the most likely given the model, given the parameters, okay? And now we're trying to tweak the parameters such that this probability, if you like, is maximized. But of course, this is not a probability with respect to W is a proper probability density if we're thinking about regression with respect to Y, and this is why we call this a likelihood function, because we think of this as a function with respect to the parameters. Okay? Probably this is stuff that you're already very familiar with, so I'm just repeating this so that you get comfortable with the notation and the motivation. Okay, but now when we have a likelihood, now we're armed with something very powerful, which is something that allows us to use Bayes' theorem to invert this likelihood function to obtain something much more powerful, which is this posterior distribution over the parameters. So by multiplying this likelihood by a prior over the parameters, now what we can do, if we properly normalize this, then we can obtain the so-called posterior distribution over the parameters. And now this is, of course, mathematically very beautiful, but computationally this becomes an absolute nightmare because the form that this likelihood has is very complicated. If you remember, if we go a few slides back here, we have a quadratic form here where f of xi enters here. And f of xi is a composition of functions where the w's are inside this composition. Right? So when you take the square of this object, it becomes something a bit horrendous that contains all these compositions, and the w's are nested inside. And now it doesn't matter whatever prior you can think of, when you multiply a prior distribution by this likelihood, you're not going to get anything that looks like a proper distribution that we know of. Okay? And so already choosing these priors in a sensible way, if you have, for example, a Gaussian likelihood with a linear model, it makes sense to use a Gaussian likelihood, a Gaussian prior, because then the posterior will be Gaussian. But now here, because the dependence on the W for the likelihood, the W enters in such a way that there's no way you can get anything analytically available. So mathematically already this is a problem, because then there's no conjugacy you can sort of exploit to obtain a posterior in a form that you like. And then we have this normalization that maybe there is another way we can do this normalization somehow, but mathematically this is not easy to do. Again, because of the same reason, W enters in a way that is very complicated inside these functions. And so now the question is, what can we do? Because this integral now lives in the number in a space that is as large as the number of parameters. And how many parameters do we have? Well, these days we have so many, right? So if we think about LLMs, we're in the billions, hundreds of billions. Okay, and I've been giving these talks for a long time about Bayesian inference and so on. This slide has been in my talks for a long time. And a few years ago, I was talking about CompNets, 100 million parameters. Oh my gosh! And now we have billions. Okay, so it gets worse every few years. because we are already at the trillion, I guess. Now with ChatGPT, already we are at the trillion. So if we wanted to be Bayesian about these models, it already becomes a bit challenging because the dimensionality is huge, and we have to characterize probability distributions over very large dimensional spaces. And these integrals are not easy to do. So, but imagine for a second that we could do this. What is the benefit of doing this? And this is exactly what I was talking about before. So the ability of these models now to be able to characterize uncertainty in prediction. So now, if we look at the predictions, we can take for a new given x star, we can predict y star by multiplying the likelihood, the predictive distribution for a given w, weighted by this posterior distribution. And if we look back at what this posterior distribution looks like, this posterior distribution starting from a certain prior excludes values of the parameters that are not compatible with the data we have, right? Because we're multiplying the likelihood by the prior, so anything that is outside of the prior is going to be put to 0 by the prior, but anything that is supported by the prior is going to have is going to be multiplied by the likelihood. And so if we have certain configurations of the parameters that do not fit the data, the likelihood is going to be very low, because remember, the loss is going to be very large, and x of minus loss is going to be very low, right? And so this is going to exclude certain configurations of the parameters. Okay, so now what we're doing, we're taking these good parameters, okay? So we have a distribution over the parameters, and this is going to have peaks everywhere that the parameters are good to fit our data. And now we're weighting the predictions by that posterior, okay? And if you think about an approximation using Monte Carlo, this is really an ensemble method. This is an average of possible predictions with models that have parameters that are all good to fit our data to some extent, okay? Because if we did a Monte Carlo approximation, we would sample from this posterior distribution and average predictions with those parameters. And this is exactly what I did in this picture. So this is the data I had before, and now you see that we have these beautiful curves, and now we have an infinite number of functions that can fit this data, and I'm plotting a few of these. I did some sort of Monte Carlo sampling here, okay? And this is for regression, and this is for classification. And so now when you give me a new x star, I'm not going to give you just a single point prediction, but now I can give you a whole distribution, which is exactly what we need in order to quantify uncertainty and to know when we don't know. Because, for example, here, where we have some overlap of these classes, you see that the uncertainty is very large. So the classifier seems to be pointing to the fact that we have maybe higher probability of triangles, but as you can see, there is a lot of uncertainty there. And so this is exactly this notion of knowing when you don't know. And this is what we need these days to say, okay, I don't have enough information to make a decision here. I need more data to be able to refine my predictions, for example, okay? All right. So I'm not gonna spend too much time here because otherwise this would be a tutorial on approximate inference methods, but what can we do to approximate this posterior distribution? So one idea is to use Laplace methods. I think Immer A-Stats 2021 is one of the approaches that I think is the most prominent in this direction, because there is some linearization of the models that is done. So this is called linearized Laplace approximation. There are some nice theoretical properties. I reviewed a thesis a couple of months ago of someone in DTU, a student of Søren, and they studied the properties of this linearized Laplace approximation, and these methods can produce Gaussian approximation to the posterior, which are somehow sensible and have some nice properties for predictions. So just to give you a simple illustration of what's going on, what they do is to linearize the logarithm of this expression and then apply a quadratic approximation to that, okay? So essentially, Gaussian approximation, add the mode with some, let's say, rotation of the covariance such that it's aligned on the manifold of the parameters. Okay. Variational methods, this is Graves 2011 is the first reference in this area. And this is really taking variational inference, write the elbow, and just run it through using a Gaussian approximation, fully factorized. So you have a Q distribution, which is a product of distribution over each individual parameter, and then letting it optimize the elbow. Okay. Again, I'm not going to go into the details of this, but this is really standard variational inference applied to neural networks. Markov chain Monte Carlo also have been developed to exploit scalability. So one of the issues with Markov chain Monte Carlo is that you have to set up a proposal mechanism. So you are in the parameter space. So even though you cannot, let me just maybe go back here, even though you cannot compute this normalization factor here, what you can do is to set up a Markov chain that actually samples from this posterior distribution. And this Markov chain is set up so that you are at a certain point in the parameter space W, and what you do, you propose a new value, and then you either accept or reject. And this accept or reject mechanism is based on the ratio between the posterior at where you're going over where you're currently at, okay? And because of this ratio, this normalization constant, which does not depend on W because it's integrated out, it cancels out. And so your accept or reject mechanism only depends on the ratio between likelihood where you're going and likelihood where you are. Prior where you're going, prior where you are. Things that you can compute, okay? And this Markov chain Monte Carlo business has been around since the 50s. Metropolis 1951, I think. Hastings then proposed this for statistics in 1970. This is why the first algorithm that you may study in statistics is Metropolis-Hastings algorithm, okay? And this idea of setting up a Markov chain is very clever, and then now the idea is how do we propose, make proposals that are actually efficient. And so people have come up with all sorts of ideas. There is Hamiltonian Monte Carlo, which was developed in the 80s, that then has been adopted here in this paper in 2014 to actually use mini batches, which seems straightforward. You know, when you have a loss, you always mini batch because it can be scalable. You use stochastic gradients. But it turns out now that if you try to do this Hamiltonian Monte Carlo where you simulate the trajectory of a particle in a sort of potential energy, so this is a sort of physical analogy that people make with the sampling, between sampling and physics. Then if you use stochastic gradients, things break down. So they have some nice theory to tell you that actually if you do it in a proper way, there's no problem, you can do it, and it's scalable, and you can scale to large data, okay? So again, I'm not going to go into the details, but if you're interested, this is a good reference to start playing around with MCMC. We tried on models up to a few tens of millions of parameters with success. So it scales really well. I mean, still not at the billion scale, but at least at the tens, hundreds of millions, I think we can do it. And then, of course, again, if you look at the predictive distribution I showed you before, you think of this as an ensemble method, then why not using ensembles directly? And so, again, the literature on ensemble methods goes back a lot, many years back. But people have specialized it for deep learning. So, for example, in this paper in 2016, they used dropout. When you use dropout, usually you do it at training time to regularize the model. So what you do with dropout, you switch off a few weights. At each iteration, you switch off randomly a few weights in your model. By doing that, you make the model more resilient to switching off weights randomly, and therefore it improves the generalization property of your model. So dropout has been used a lot in training deep learning models. And so what they proposed here is very simple, to just use dropout at test time. Because usually what you would do at test time, you would not use dropout. You would just use all the weights. But actually the idea here is to say, well, I do a few iterations where I predict by applying, again, some random pruning of the weights. And then what I get in the output, I get an ensemble. And this ensemble gives you some uncertainties that we can actually use for decision making, as I was motivating at the beginning. And of course, now the question is this Bayesian anymore? I mean, you're doing something which is a total hack. You know, you have a dropout at training time, you do it also at test time, and you're good to go. Actually, it turns out that they made some nice connections with the variational inference. So you can view this dropout business as applying dropout, as a variational inference where your posterior distribution is some sort of weird mixture of Bernoulli distributions. Yeah. Okay. I'm not going to go into the details, but geometrically this is a bit weird. But they managed to make a connection with variational inference. So they could write an elbow and show that this Monte Carlo dropout is actually optimizing this elbow. And then there is this deep ensemble method by this author. I cannot pronounce the surname. I know him as Balazs. Okay, so let's just call him that. And this is the famous deep ensemble method, where you say, let's take a model, and let's randomize the initialization. And then when you optimize, you end up always in a different optimum. And for my friend Balazs, this is an ensemble. And then you can use it to make predictions with uncertainty. And this surprisingly works really well. And as far as I know, there's no connection with any Bayesian inference business that we know of. Okay, but maybe the theory will be developed soon, and maybe people will come up with the result saying, "Oh, this is actually variational inference or something." Okay, and this is again, one of the complications with working with neural networks is that whenever, the amount of possible invariances is huge. It's very easy to show that if you take any neural network, you just switch weights around in a certain way in the layers, you can obtain the same output. Okay, so it's very easy to show that there are invariances, and they grow so much. The number of these invariances grow so much with respect to the size of this neural network. So it's very easy to end up in different modes in the posterior. They may represent the same thing, but also because these models are extremely nonlinear, they can also represent, slightly different modes. They can represent different things. Okay, so, and this ensemble method actually works remarkably well. Okay, so this is a bit of a timeline. I think I started. Yeah, so I think this is a nice timeline just to give you a bit of an idea of how this field of Bayesian deep learning developed. So people started talking about Bayesian neural networks since the 90s. So this would be Dave McKay, that talked a lot about neural networks back then, how to do Bayesian inference, and how to do Bayesian inference for deep neural networks. And at the time, it was proposed to use Hamiltonian Monte Carlo, but of course, computing was very expensive and not very powerful back then. And then another important contribution was in 1996, this connection between deep neural networks and Gaussian processes. I will be talking a little bit about Gaussian processes later, but essentially these Gaussian processes are stochastic processes that you can use for machine learning, to do modeling of any kind. And essentially this result shows that if you take a neural network with one hidden layer and you push the number of neurons to infinity, you can obtain, by putting a distribution over these weights, you obtain something which is a Gaussian process, which essentially says that the marginal distribution and the joint distributions of your output are all jointly Gaussian. Okay? And this is important because this establishes a connection between these mysterious deep neural networks and something that we actually know very well, which are Gaussian processes, which are essentially some form of linear models where you push the number of basis functions to infinity. Okay? This is another way you can view this. And this is something that we can easily deal with computationally. We have a lot of machinery here. And interestingly, I think a lot of the literature in the last few years actually use this type of connection to port results from one literature to the other. So we've done some work that was used to scale Gaussian processes to actually do deep neural networks faster, and people did the same the other way around. So people used a lot of ideas from deep learning to scale Gaussian processes. Okay, so there has been a lot of cross-fertilization in the last, I would say, 10, 15 years in this, and we've been part of this type of literature with a lot of work on Gaussian processes. So as I was saying before, Graves 2011, this is the first work on variational inference for deep nets. That's a break, right? Okay, so because in Saudi this would be a praying break or something. Yeah. No, it's okay. I mean, if you guys are okay, we can continue. Yeah. Yes. I'll drink some water. Right. Okay. So I was saying that the first work on variational inference for deep nets is 2011. This is actually a mini batch version already. So again, one of the main things that really changed the game for deep learning was this idea of using stochastic optimization. And this stochastic optimization you can achieve by taking the loss, which is a sum over all your data points, and say, okay, now I use only a subset, and this gives me an unbiased version of my loss. And if I take the derivative of that, of course, I get an unbiased version of the derivative. And the unbiased version of the derivative is a stochastic gradient. And stochastic optimization has nice properties. You can obtain convergence to local optima and all that. So this is very powerful. And of course, in Bayesian statistics, this was not very much adopted until recently, you know. And so when people did it in deep learning, of course, we also have to do it in Bayes somehow. And so this is the first attempt to do it in variational inference for deep nets by Graves in 2011. Then I was mentioning this 2014 paper by Chen and others. This is Emily Fox's group that did this, but also at the same time, Iwaite and Max Welling, they were doing the Langevin dynamics, stochastic gradient Langevin dynamics paper, which is a beautiful paper to read. Very difficult to implement, but it's similar to this stochastic gradient optimization algorithm, except that you can think that these Langevin dynamics algorithms are one-step Hamiltonian Monte Carlo methods. Okay, so let's not go too much into the details, but around this time, just to say, around this time, people were excited about the stochastic sampling methods. And of course, the big game changer, most of you are too young maybe to have witnessed this, but I was at NeurIPS 2015, December 2015, when someone at Google actually made a big presentation about TensorFlow, and we were all quite excited about, because automatic differentiation has been around for a long time, and now we all take it for granted. But actually, the TensorFlow was I would say, the first environment that really allowed us to exploit this automatic differentiation for these deep learning models. So this was huge, because now you don't even think about it. You implement an objective function, and derivatives are done for you. Someone does the derivative for you. TensorFlow, now maybe PyTorch if you're more into that. But we don't think about it. But when I was your age, I was actually writing an objective function, writing down the derivatives, implementing the derivatives, debugging the derivatives, because it would take me a while to get them right. And you know, it would take a while. Now you don't even think about it. You change the loss function, you change the objective, boom. Everything is done for you. Even the optimization is done. You just call Adam and AutoGrad, whatever, all done. So 2016 was this big game changer. So it's 10 years now that we have this, we're used to this fast development cycle where we can easily optimize and do things. And of course, as Bayesians, we never optimize. I mean, Bayes' theorem doesn't say max, argmax anywhere, right? We have integrals, multiplication of likelihood and the prior. But of course, if you cast now inference through variational principles, then okay, the variational objective becomes an elbow, and now you optimize this elbow, this evidence lower bound, with respect to a distribution. So you parameterize the distribution with mean and variance, and now mean and variance of that distribution become the parameters that you can optimize over. And now you can do all the stochastic business of stochastic optimization and so on. So this is a nice, let's say, project that you know, if you're interested in working on this type of field, you can easily implement your variational inference in a very general way, where you just have to, you can just replace the loss function, you can replace the model, you can make it linear, non-linear, neural network, whatever you want. And then the machinery underlying is always the same. It's just optimization of an elbow. And the elbow changes depending on your options, and it's beautiful, it just works. And of course, linear models, for linear models, variational inference would give you can give you the exact posterior, right? So you can even verify that this actually is the case, and you can play around. It's a lot of fun. Highly recommend that if this is something you you're interested in working on. And then, so from 2016, this was the first Bayesian workshop on Bayesian deep learning. 2016, at NeurIPS, I was there, huge crowd, hundreds of people, and also this paper I was mentioning before by Yarin Gal and Zubin Garamani on dropout as variational inference. These were the first works that really sparked the interest on Bayesian deep learning to the extent that we have today. And I would argue that this was this work here, dropout as variational inference. Okay, let me go back. So if you use this approach on a convolutional neural network, take a ResNet that you like, run this variational inference for deep nets here, it's not going to work. Many reasons why it cannot work, because of the factorized posterior, many parameters. The elbow, gives you something that is over-regularizing. So you have a lot of problems. And so the first approach that actually worked was dropout. Monte Carlo dropout, as they call it in this paper. So when I was writing a paper about, when we were trying to do something with convolutional neural networks, we were trying to do sampling and so on, I had a reference for this 2016 paper as the first one actually working on Bayesian convolutional neural network. And my collaborator asked me, I cannot believe that there is nothing before this that was doing a Bayesian ConvNet. But actually, nothing would work before that, right? So we just fast forward a few years. We've done some work to actually improve variational inference to make this work. So we have some papers in 2017, 16, 17, to actually improve variational inference for these deep network models. But another issue arises when we work with these models. Apart from the fact that, a lot of people, if you go around and you say, I work on Bayesian deep learning, Bayesian statistics, Bayesian machine learning, the first thing that people ask you is it not too slow? This is the first reaction that people have, that there is this myth, I would say, that Bayesian methods are slow. And so there's no point in working on them because they're slow, all right? And I would argue that if you optimize models, it's also not that simple, because you have to optimize a lot of hyperparameters. There is one, let's say, truth to the fact that maybe Bayesian methods are slow, because again, if you think about having to deal with ensembles, when we make predictions, we predict with multiple values of the parameters. This means that we are doing a forward pass with our model many times, as many times as we want for this ensemble to work. So if we use an ensemble of 10, this means that we need to use 10 forward pass. With optimization, once you optimize the model, you just do one forward pass. So there is some truth in that we have to do more work. But actually, I wouldn't say that it's more difficult to tune these algorithms compared to optimization. If you look at many implementations of optimization methods for deep learning, they have magical learning rates, schedules, and things, mini batch sizes picked from the air, you don't know. If you change these things, nothing works anymore. So I don't think that the Bayesian methods are particularly more difficult to optimize or to tune compared to these methods. But actually, the thing that was reported a lot in the literature, especially at the beginning of this wave of Bayesian deep learning in 2016, is that predictive performance is usually worse. So people started questioning, is Bayes optimal? Of course, there's nothing suboptimal about Bayes. Bayes is optimal, but there is some other problem here, that Bayes is as good as what you put in it. So you have likelihood and the prior. And if we establish that the likelihood comes from a loss, and people use this loss all the time to make it work, to make deep learning works, then of course maybe prior is the problem. So people came up with all sorts of approaches. The ensemble methods I was talking about before is one of those, is one wave of works that tries to go around Bayes, because they say, well, Bayes is not optimal, so we don't like it, so let's do something else. But there's nothing wrong with Bayes' theorem in itself. Okay, so this is sacrilegious to say that Bayes' theorem is suboptimal, or it doesn't work, specifically for deep learning. So I would argue that the problem of choosing sensible priors has been massively overlooked, and this is what we worked on. So this is something now that I will be talking about briefly. So we still have 35 minutes, right? So we stop at 2:45, correct?
Yes.
Okay, so I will also I will want to leave some time for questions, so I will maybe not spend too much time on this. But just to say that choosing sensible priors for Bayesian neural networks is not easy. Again, precisely for the reasons that I was talking about before, so that these models are very intricate, very complicated, and that the choice that you make in one parameter inside this network has some effect on the output, but it's very difficult to understand what is the sensitivity, if you like, of these choices. And so when people don't know what to do, what do? Standard normal priors. You know, when you have to choose a Gaussian distribution, say Gaussian with 0 mean and standard deviation 1. So this has some problems because depending on what activation function you put in the network, this may lead to something that gives you exploding variance. So people started to think, okay, maybe we can downscale this effect by the number of neurons that we have incoming to a neuron. And if you do that, this is what people call Hay initialization, I think, in deep learning. Okay, so to avoid initializations that make the parameters go wild. And with this, you get something which is now a bit more meaningful in the sense that the output at least don't blow up. But this is an illustration of what happens if you now look at what is the output of these models when you start choosing these standard deviation for the prior over the weights and the standard deviation for the prior over the biases. So we assume 0 mean again, just to make the output to be 0 mean. But you see that the kind of functions that we obtain in the output somehow are already kind of pathological, and it's not very easy to establish what is the dependence of these parameters with respect to the output with respect to the parameters. You can see that for some choices of the parameters, the covariance of the functions in the output is completely constant, meaning that we obtain these functions that are quite flat. If you know anything about simplicity bias, I think this is a good intuition that somehow this central me theorem kicks in at some point and gives you something that is very simple. Okay, and this happens also as we increase the model size, as we're going to see in a minute. But I wanted to just briefly mention that I worked many years with Gaussian processes, and the reason is that they are beautiful. They are beautiful models to work if you are interested in priors over functions. Why? Because we have parameters here that give us some intuition about what we're doing. So we want to, by choosing a certain covariance function, we can impose properties on the functions that we can sample from these models. Okay, so for example, for this choice of covariance function, we can obtain functions that are infinitely differentiable. If this is something we want to impose in the prior over the functions, then of course we can make this choice. And these parameters here, this L parameter determines the so-called length scale of the functions. So as I increase the value of the length scale, I obtain functions that have longer periods. If I reduce this value, I obtain things that have very short periods. Okay. And then, of course, I have this scaling factor in front that I can use to actually scale the marginal variance of these functions. For these Gaussian processes, one of the limitations is that all these functional realizations are all Gaussian. So marginally, each distribution here for each one of these infinite number of random variables is Gaussian, and jointly they're also Gaussian. And of course, this is a limiting factor now because life is not just Gaussian, right? And now the question is, can we marry these two ideas? So this was the simple idea we had. Can we take the power of this Gaussian process formulation that is very natural for thinking about priors for functions and marry it with the power of deep learning, which is very expressive and very powerful in getting strong models to do good predictive performance, to obtain good predictive performance. So the idea is that, well, these models work in function space. So whatever we decide here determines the properties of the functions in the function space, in the output of the models. But when we choose priors for neural networks, we choose priors for the parameters. And these choices are very difficult to interpret. So the idea is to marry these two ideas by saying we can sample easily. So we can sample parameters for these neural networks, and we can see what the outputs look like. So this is what I did in this picture here. I can easily sample, okay, parameters and then see what functions I get in the output. With the GP, with the Gaussian process, I have a form for what the output looks like, and how do I match these two now? In the function space, I want to be able to match the samples I obtain from the neural network with something that looks like a Gaussian. And the problem is that we don't know what the closed form density for the functions obtained by the Bayesian neural network is. Again, because we have things that are highly nonlinear, and parameters enter in a very complicated way in the formulation of these models. So the first idea would be, why don't we just minimize the divergence between the distribution over the functions that we obtain with the neural network and the GP? And the problem here is that we obtain this entropy term. If we do that, then this entropy term is intractable, and it's very difficult to estimate. To obtain estimates of this that are accurate is very difficult. So this was tried by David Duvenot in 2017. They tried something like this, and it didn't really work. So we came up with a different idea, which is based on optimal transport. I won't go too much into the details, but we use the Wasserstein formulation, where we say we minimize some form of discrepancy, if you like, between the expectation of functions of the inputs that we can obtain, where these functions here are one Lipschitz. Okay, so we take the supremum of an expectation, and this is reminiscent of what the GANs do, and I will be talking about generative adversarial networks in a minute. But this is just to say that to compute the discrepancy between this Wasserstein divergence between two distributions, what we need to do is to do an optimization problem. Okay? And this is where the adversary of GANs come, if you like. In this case here, for the one Wasserstein, we come up with one Lipschitz functions that are the discriminator. And we have to look for the function that discriminates the most samples from the two distributions. Okay? Again, I will be talking about this in a minute when we talk about GANs, but just to give an idea that this is grounded in optimal transport, if you like. Why is this good? This is good because we don't need to know the closed form for pi and nu. In our case, this is the functions that we obtain from the GP, and the distribution over the functions obtained by the GP and the neural network. We don't need to know the closed form. We just need samples to be able to optimize something like this. And now the problem is, how do we optimize with respect to one Lipschitz functions? So this is typically what people do, is to parameterize by a neural network. And now the idea is to say, let's minimize this one Wasserstein with respect to the parameters of the prior of the neural network. Okay? So what we do is to tweak the priors over the parameters of the neural network so that the output is going to look like the Gaussian process. So this is fully sample-based. Again, we don't need to know any closed form for the neural network. We don't need to target Gaussian processes. If you have your favorite physical model for whatever process you are interested in, you can use that in place of the GP. And then this is just an illustration of how it works. This is a Gaussian process prior with some length scale, and these are a few samples. And the optimization, as you see, is going to make the neural network produce samples that look increasingly like the Gaussian process priors. Samples. Okay? Great. Okay. Okay, so now just to give you just a feel for what kind of results you can get from this. So this is the GP prior. This is the Bayesian neural network with fixed Gaussian priors. And this is with the normalizing flow priors. Okay, so to make it more flexible, we can even go crazy with the priors and make them more flexible. And so a neural network that parameterizes the parameters of a network, right? And then if we do this optimization, so we try to optimize this type of priors and this type of priors to this Gaussian process, we obtain these two pictures here. You see that, of course, the normalizing flow prior is very flexible, and you can really match very nicely what the Gaussian process does. And so now this is the curves of the objective that we minimize, okay? And now let's see what kind of performance we will get on a synthetic data set. This is a data set with a gap in here, in this part of the space, so to see what happens with the uncertainties. And Gaussian processes are so nice because they are able to capture this uncertainty when there is no data. You can see here very nicely out of distribution. So GPs are very nice to tell you when the model doesn't know, right? But of course, if you use these fixed priors that have these properties of giving you these priors that are very flat and very simple, let's say, functions, of course, in the posterior, you're not going to get anything different. You're going to get very flat uncertainties there. But of course, as soon as we introduce these optimized priors, then we obtain something that behaves more like a GP. But now we have a neural network, so this is a much more flexible model that can handle, of course, scalability, flexibility, and so on. Of course, we also did it for CombNets. Here we were sampling with the stochastic Hamiltonian Monte Carlo method I was telling you about before. I will not go too much into the details. Of course, if you're a deep learning ninja, you will be criticizing me because I show you 87% on CFAR10, when now it's easy to do 99 with any other model. But of course, we were not doing any data augmentation here. We were keeping it very simple just to isolate the effect of changing the priors here, okay? And so you can see that by using this optimization idea of optimizing the priors, we get much better performance compared to other models. So this is pretty much what I wanted to say, just to advertise this work on thinking about good priors. I think it's something we need to think about when we're Bayesians. And maybe a good time to take one or two questions now, and then I can move on to the second part of the talk. Otherwise, we can get the questions for later. I can ask. I think I maybe want to ask deep learning. This one.
Yeah, that should be.
And I keep it pressed.
Oh,
yes.
nice. Okay. Yeah, we can hear you now.
Okay, so we did this work in 2022, and lately we've done some work on trying to understand what happens to uncertainties when we scale the models to large number of parameters, large number of data. So the literature on scaling laws that you may know of tells you that you should increase the model size to get better generalization properties. And this is why models are becoming bigger and bigger. And this is why there is a race on making them huge and increasingly bigger, because generalization error for a given training cost is going to improve. And so we did something similar for uncertainties, because it would be interesting to know when epistemic uncertainty, which is the uncertainty that you get from the posterior. So this epistemic uncertainty is measuring how the model is uncertain about your predictions by looking at the diversity of the ensemble, if you like. Of course, when you have infinite number of data, we know that in parametric models, identifiable models, everything is nice and easy. The theory tells us that the uncertainties shrink by the variance goes with 1 over n. So as we increase, if we double n, we half the variance on the parameters, which means that we half our epistemic uncertainty, to the point where this epistemic uncertainty will become so small that there's no point in doing Bayesian inference. So our question was, okay, does this hold in deep learning? Of course, these are parametric models, but they're not identifiable. So all this theory of Bernstein von Mises doesn't work anymore. So the rate at which the parameters contract is no longer 1 over n. The rates are different, and the models are big. So you need a lot of data before this epistemic uncertainty becomes small. And I can tell you for a ResNet 20, 28 or something, I think you need around 100 billion images before your epistemic uncertainty is such that you are on the second digits in your predictive distribution.
Yeah, also kind of when you look at modern LLMs, okay, you can claim that they can do everything, very high quality, but in reality, if you are clever enough to kind of to find a very specific problem that kind of was not mentioned before, LLMs become very dumb even given the training scales. Like, okay, what I recently discovered, you can draw kind of ask it to draw a goose in ASCII to characters, and the results are terrible. Or kind of more serious problem like to design a kernel for better multiplication if the size of matrices are bigger than you would expect, and that implemented in the literature. Okay, and the second question, okay, I suppose this also pretty common for your talks about the kernel selection and what was specifically used in this paper.
Yeah, great. The great question. Again, I mean, we didn't go fancy on choosing kernels for the GPs. Again, the point here was to say, is there any way we can make priors sensible by not being so pathological? Mm-hmm. So in a way, I want to use my two hands, but okay, it stays. So in any applications, if your likelihood says that your parameters are good here, but your prior is over here, what's going to happen is that when you multiply likelihood, which is here, and the prior, which is here, you're going to get a posterior in the middle. Not what you want. So you want to have a posterior that is able to somehow move closer to where the likelihood is, right? And for the kind of problems we were considering, we were not expecting that the data would be so flat that these priors would be any good. So we're really trying to move our prior closer to where the data will probably be, right? So to be more sensible about the kind of... So what I'm trying to say is that it doesn't really matter how precise you are in optimizing this Wasserstein objective. It doesn't really matter what kind of kernel you choose. I mean, you can even do this maybe without optimal transport, even just saying, okay, let's try to find an objective that matches somehow, measures that the covariance that we get for the functions is similar to the one we get with the GP, and the mean is 0 or something like that. And this should also kind of work. You see, it's just about making the prior, like, move away from these very pathological priors.
So kind of as long as you have kind of pretty rich family of functions induced by this prior or kind of induced by the kernels, that everything is okay.
Yes.
Okay, thank you. Any other questions?
Yes.
Yeah. Who is the volunteer?
Yeah, thank you for the first part of the lecture. As I understand, the wave space geometry is quite difficult. Let me explain what I mean. We have like lots of connected regions, valleys, and very different wave vectors can represent almost the same functions. So how can we be sure that our approximation will capture all decision-making relevant functions? I mean, the sampler can move substantially, but we will not get like any real progress. Do we have some approach to find this so it's maybe closer to some like kind of interpretability of this geometry?
Yeah, I mean, if I understand your question is, can we move away totally from just handling parameters in the first place? Can we just not think of function spaces directly?
Yeah.
But again, this is a matter of parameterization. I mean, if you think of these neural networks as just parametric ways of determining what a function should be, then parameters are essential in a way. We have to go through the parameters to be able to do things. Of course, a lot of people are talking about ways in which we can do maybe predictive posteriors without having to deal with parameters in a way. Working in function space, I mean, there are some works that try to do that, but in a way, I'm not convinced that they bypass the need to specify something about the parameters ultimately. So the formulations can be done in function space, but ultimately you have to interrogate these models. You have to specify the parameters somehow. Okay. Right.
Thanks.
Maybe that's just.
I'm just trying to understand a bit. So, is this a function space prior? So it's because I know in the weight space there's massive symmetries, massive, and that kind of throws out any sort of standard approach. And you get around it with a function space prior, but I'm not sure.
So what we do here is to really tweak the priors of the parameters so that the outputs look like the functions we want. Essentially, that's it. But we still in essence we optimize.
Oh, so the functions you're sampling and you're looking at them and they're what you want. So therefore, it is a function space prior, in effect.
Yes.
Yeah.
But okay. we do it through specification of priors over the parameters.
Yeah. All right. What about? I mean, I understand these stuff are discrete, and you were giving us the example of continuous. So, is there a sort of a challenging mapping there, or what's the?
You mean when we deal with classification?
Yeah, so there's a sort of multivariate.
Yeah, I mean, I didn't show the priors for classification problems, but of course, it's the kind of flatness you see here in those green priors there. You also obtain for class labels. So you have when you sample a function.
So there's the class probabilities over the.
Yeah, they become sort of degenerate on one class specifically instead of covering. So you want to obtain priors that maybe. Over the class labels are uniform, and so.
All right.
Yeah.
Thank you.
Yeah, thanks. Okay, let's maybe move on. Let me switch this off. Yes, can you hear me? Yes, good. Okay. Now this is the fun part. As I was saying before, I was hoping that I would speak faster, but of course, when you give me the floor, I just go on and on about stuff. So maybe this is going to be only a few minutes, but I just wanted to give you this idea of how to understand certain kinds of models that to me look like a complete hack by thinking about probabilistic principles. So when we think about generative modeling, of course, a closely related problem is density estimation. We have a problem where we have some random variable x, which is distributed according to some p of x, and we have samples. And we want to build some form of model for this p of x. Let's call it p of theta of x. In density estimation, we want to be able to evaluate this, but in generative modeling, we don't care about actually being able to evaluate. We can even implicitly build a model that is able to give us samples that look like the ones from p of x. Okay, so this is just, when you see these kind of pictures, it's crazy. Because these are models that have been trained on this famous FFHQ data set. And this is the kind of samples you get. Okay? Maybe for you it's not that impressive because now you're used to generating images with Gemini and so on. But to me, this is really very impressive. As people working in statistics, we should all be very impressed. Because this is sampling from an extremely large dimensional and structured p of x. Why am I saying structured? Because we know that these very large dimensional images, natural images, live on some sort of low dimensional manifold. And so these models are really able to capture that manifold and really give us samples that look very much like things that are natural. It's insane. What's the advantage of GANs with respect to other models? And why people got excited at some point? Because you just need one model evaluation to produce new samples. When you use diffusion models, you solve stochastic differential equations. when you train the model, but also when you want to generate new images, you also need to, let's say, forward simulate stochastic differential equations, which requires you a few steps of interrogation of a neural network. Here it's one shot. When you train the model, then when you want to generate a new image, you just do it with one forward pass of the neural network. So this could potentially be the advantage of using these models compared to diffusion models. So this is last year, I asked Gemini to give me that kind of picture to explain GANs. Okay, so this is the typical thing, is that you have a generator. It's a random guy that draws random things. And then there is a discriminator, which is the serious guy now, that tells, oh, this is a fake, or this is a real image. So the discriminator is presented with the true and the fake images, and it has to classify these appropriately. And of course, as the discriminator is giving feedback to this generator, the generator has to improve and draw things that look more and more like the real ones, to the point where the discriminator doesn't know, that cannot tell the difference between the two. So this is already a very complicated construct, because now you have two neural networks. You have a generator, neural network, and a discriminator. It's a two-game type of problem. So, game theory people have got excited because does this process converge or not, and so on. It's a major pain. Okay, so if you've never worked with any of these models, let me tell you, this is a huge pain to work with these models. There are lots of issues. Of course, if the generator copies exactly some of the images that were in the training set, then the discriminator cannot tell the difference because they're exactly the same. So these mod collapse problems happen a lot. So you have to be careful how you set up the optimization and so on. I asked Gemini 2 days ago to generate a new image. Now this has become much better. In 1 year already, you see more details and so on. Of course, images of cats. This is the, and now the serious guy became owl there. But to me, so if you look at any implementations of GANs, there is batch size 32, learning rate 0.00002. If you change by an epsilon, any of these things, training doesn't work anymore. Models don't converge. You get divergence, a mess, and it's been a pain, right? And so this feels to me like people came up, woke up in the sleep, and they came up with this very specific numbers of hyperparameters to train these models. And this is a cartoon, again, that Gemini produced for me. And for me, when I try to understand these models, I started thinking about latent variable models. And again, this is an illustration a year ago. The text doesn't make any sense. So if you try to read it, it's very funny because it doesn't make any sense. So in latent variable models, you have some latent factors that produce this observed data. And these latent factors are typically, you would hope that you find these latent factors that are minimal and exhaustive in being able to represent all the diversity you have in the training set. But mathematically, then let's start thinking about a generative model with latent variables, how it could work. So we could have latent variables, one for each of the data points. We have a prior for these guys. And then we can generate, we have a neural network that, given this Zi with parameters W, produces an object, an image. So then if you start thinking about this type of construct, the likelihood you would get is something very strange. If I don't add any noise here, if I'm assuming that deterministically these xi's are generated, if I try to think of a model that produces this type of, a probabilistic model that produces this type of outcome, then I need to assume that the likelihood is a delta, a Dirac delta, which is going to give me a 1 only when I generate something which is exactly in the training set. Okay, but let's, for now, start from this modeling assumption. Again, if you ask, I asked 2 days ago, latent variable models. Apparently, the latent factor here is the happiness of kids and their outcome in social life, laughing, playing, and so on. Okay. And so now, with that kind of model, we have a few options. With that kind of model, we have latent variables. We have a neural network that produces X. And now, if I wanted to be, consistent with what I told you about before, we should be Bayesian. Let's put a prior over all the parameters, and this would be a fully stochastic Bayesian neural network that now produces my images. Or I could be partially stochastic. So there is some interesting work that happened recently, in Sharma 2023, that says that we don't need to be stochastic about all the parameters in the network. Just a subset is enough to be able to express any conditional distributions of x given z in this case. And this is very influential because what I was telling you about before, Bayesian inference is hard when we have billions of parameters to deal with. But if we only have a handful of parameters to deal with and the rest are optimized, maybe these hybrid networks where some of the parameters are stochastic and some are not, maybe these are easier to work with. And this is some sort of exciting field that we're dealing with today. But with GANs, actually, it's the other way around. Stochasticity is not on the parameters. Stochasticity is in the inputs. And the network is deterministic. Okay, so you can think of these three models now, three options based on what we discussed before. And now the question is, which one should we consider? Well, first of all, these are all stochastic neural networks one way or another. In this case, it's fully stochastic. In this case, it's first layer stochastic. In this case, it's input stochastic. But it turns out that the theory tells us that under certain conditions, which are quite mild, actually, well, of course, we need a universal approximation of the neural network itself to be able to have enough, let's say, capacity. But the nice thing is that under very simple conditions, maybe not easy to verify because universal approximation sometimes is not very easy to verify, but we can represent any p of x that we want with these type of models. This is very powerful because now we don't need to be fully stochastic. We can be partially stochastic. And now also, if this is the GAN, we can also think that maybe there are other ways in which we can implement GANs that are not going to be so poorly performing. And so maybe just to give now switching from those diagrams to graphical models, speaking under the supervision of Ray here, this is the three models that we saw before. So the GAN would be something that has one latent variable per observation. We have n of these observations, x is observed. And now we have parameters that allow us to determine the x given z and w. And then maybe these w's now can have hyperparameters, okay? And these hyperparameters here, if we treat w as fully stochastic, fully stochastic, then we obtain the so-called Bayesian GAN that was proposed in 2017 by Sachi and Wilson. Instead, the standard GAN would be something like this, where you have the latent variables and the observations. We have n of these guys, and w now is optimized. Okay, so there's no circle here because in this notation, these parameters are optimized. And the other way would be to say, I have a neural network where z now is no longer there. All the stochasticity is in W, and with the stochasticity in W, then we have a Bayesian neural network that produces the observations. And this is the so-called Bayesian autoencoder that we worked on with my students in 2021. Under suitable conditions, all these guys are valid ways to do GANs, to do generative modeling, right? And so now the question is, which one should we choose? And so this now becomes a model selection problem. Okay, so I'm not going to go into the details of that, but I just wanted to spend a second to convince you that that model that we came up with, where we said, take latent variable z with prior over the z, which is standard normal, likelihood, which is degenerate delta, write the likelihood, and we can integrate out the latent variable z. And with some manipulations, what we can get is that the maximization of this loss function with respect to w is equivalent to minimizing the KL between the true p of x and the p of x that we can generate with our model. Okay, so it's very simple manipulations that you can find in the paper. But just to say that what we can do here is to integrate out the latent variables. If you've ever seen probabilistic PCA, this is exactly the same thing. In probabilistic PCA, you have a linear model for the observations given latents and parameters. Everything is Gaussian. You can either integrate out z or you can integrate out w. You obtain a likelihood, you can optimize, and then you retrieve PCA. Okay? Very simple. Okay, but now the key observation is that this maximization of the expected log likelihood is equivalent to minimizing a KL between p of x and p of x. P of x, the true P of x, and the one we can generate with our model. And now this is the key, because now we can replace this matching objective from the KL, we can change it and make it Wasserstein. Or we can make it Jensen-Shannon divergence, F divergences, and so on, MMD. And as you change the objective, actually the training of this simple model that I just showed you before, where you have prior over the Z and the neural network producing the observations, gives you all these different GANs that exist in the literature. So we have one probabilistic formulation to derive all of these guys. But now we have something more. Because we interpreted this as a Bayesian neural network now with partial stochasticity, we can use the theory of Bayesian neural networks with partial stochasticity to show that these GANs are universal approximators of any P of x. This is very powerful. We have a simple proof for this now, based on this connection with Bayesian neural networks. But also now we have a problem, because we are essentially optimizing we are doing maximum likelihood optimization, because the parameters are optimized, and we can give enough, I'm not going to spend time on this, but you can see that this type of integration, when we integrate out the latent variables, still leaves the parameters free. So we are free to parameterize our model very flexibly by, we can put our P of Z, we can transform it with this model. When we have a P of Z, with these models, we transform it into a P of X, which can be arbitrarily complicated, okay? And so there's no control on overfitting, because there is no way to regularize over W. GANs don't do that. There is no regularization over W. But actually, GANs actually a bit do this, because, of course, they started noticing that this type of objective wouldn't work, so they have to regularize using gradients and so on. Anyway, so I wanted to spend a bit of time on that, but I think we're tight with time, so I just wanted to give you an idea of how we can improve these models now. So remember that before we had the delta likelihood, so we had a likelihood which was the delta of the difference between xi and the functions and the objects that we can produce. Now let's just add some noise. So the likelihood now is Gaussian. It's not just a delta. Nobody uses delta likelihoods in Bayesian statistics, right? They're terrible to work with. Let's relax. And nobody in GANs would do this, because why would you add noise to your images? It's a terrible idea. It actually works, because now statistically understand that we are using a likelihood which makes more sense than a delta. And of course, people have talked about gradient regularization. Of course, you can use small, if you take any implementation of GANs, they use small batches because they allow them to obtain flat minima, which is what we want. I will not go into the details of that. And of course, Bayesian inference also was proposed as a way to regularize. If you put a prior over the parameters, you somehow regularize the problems, right? Okay, so I won't go too much into the details. I'll show you just one picture, one table and one picture, and I'm done. So what I'm showing here, FID, the lower the better, okay? So this is this is the original GAN, let's say. This is a Wasserstein GAN with the deep convolutional networks on MNIST, I think. So you get a certain FID score, and then L1 here is the eigenvalue of the Hessian of the objective at the optimum, and the larger, the sharper, the larger this number is, the sharper the objective. As you can see, as we introduce regularization, the FID gets better, and also the flatness improves, except for this gradient regularization that doesn't do much in this case. Again, I can show you on the CFAR, FFHQ, CELEB, and so on. Similar story. But then this is the R3 GAN, which came out NeoRIPS 2025, I think. So of course, reviewer number 3 asked us, but you didn't do it on the latest state of the art, so your results are useless. So we took R3 GAN, which runs for 7 days on 2 GPUs. And now I ran 5 times everything. And so this is the standard R3 GAN. This is FID over iterations. So you get the black curve. And of course, if you introduce some regularization here with Monte Carlo dropout with different rates, we improve the FID. And this is small improvements, but of course, this is a hugely engineered architecture. So improving even by just a little bit this FID score, believe me, is not that easy. So here you also have a box plot over 5 iterations. Okay, so just to conclude, I just wanted to maybe tell you a little bit about this story that Bayesian deep learning is challenging but fun. This is why we're employed, at least so far. We're an active community. We have position papers now. We're writing a book on Bayesian deep learning. And my goal is to understand, with this beautiful music, I can say, our dream is to improve and understand better deep learning through Bayesian principles. Thank you so much. Sure.
Okay. Thank you for your talk. My question is, can you somehow explain in easy terms from maybe a geometric perspective what is better in the process of injection of the noise in different layers, not only in the first one, because maybe it would be higher dimensional, or maybe would have other Lipschitz constant when we are looking at the dependence on the output on the input.
That's a great question. Thank you. I think this idea of adding noise, of course, is something crazy, but some people tried, of course, and I think the style gun does exactly that. So
yeah, exactly.
I think it's each layer of the representation tries to capture different styles in the images, and the idea, I think, is to introduce this type of regularization inside these layers as well. So I think that's understanding how this changes the geometry. I think is not an easy thing to do. Okay. I think it's a great question. I mean, generally, my understanding is that the changing the likelihood in a way that you add noise, at least in the last layer, what it does is to just smooth the loss landscape and makes it easier to optimize. Although we haven't seen this as I haven't found a consistent way to optimize better by introducing the noise. I think it's more that statistically you get better performance because you get better generalization, because it's regular. I mean, if you don't regularize, when you see a model that doesn't have any regularization, of course, the first thing you have to do is to do it. And now the question is, what kind of regularization can we do? And now that the machine learning literature gives us a huge variety of choice, and what kind of regularization should we introduce, I think depends on the properties we want to see. And I think for me, seeing a likelihood that is degenerate this way was an enormous red flag to say, okay, yeah, we should do that. But then, of course, some other people did a lot of this regularization through gradient regularization. So they introduce a term that penalizes gradients to explode, which also makes a lot of sense because it's another form of regularization. And now, so the other thing is this regularization sometimes is imposed on the discriminator only, not in the generator. From our theory, all this regularization should be on the generator. The discriminator is an accessory to compute the objective, because if you don't use Wasserstein, for example, and you just did the KL, there's no need for the discriminator. Okay, if you see this equivalence here that I put in this slide.
So the regularization actually makes it not a true KL problem.
Makes not
what? It makes the discriminator not the true KL. But
yeah, but that's the thing. The discriminator is only an accessory, and so now, whenever you try to regularize the discriminator or make it not too strong at the beginning of the optimization, these become all optimization problems, let's say. But statistically, what I could see is that, I mean, at least the likelihood is problematic.
Yeah, so true Bayesians just use a more theoretically founded option.
We hope to do that, right? So so we're a big community of trying to do this, right? So use Bayesian principles to understand. So there was a beautiful keynote at the ISBA a few weeks ago by my friend MT Khan on using Bayesian principles to derive better optimizers for deep learning, and this stuff works. So just to say that there are different ways in which you can think about these things. In my case, for example, we've done some other work where we did the optimization of the parameters, the intensity of data augmentation. So you have a problem, you do data augmentation, but you have to choose how much intensity you want to impose on this level of augmentation. So we cast this as a model selection problem. We have an elbow, we optimize the elbow. It's very simple, but it's grounded on variational principles, on Bayesian principles, and it just gives us a way to do things better, right?
Could you please go again through this slide?
Yes.
You told that the typical gun, the default one, has a prior in the form of delta function. In which sense? And is it the case when the noise is injected only in the first layer?
Yeah.
Right?
So you have Z has a distribution. So you have that P of Zi. Okay.
Okay.
And so this integral is, of a product is.
Only one term.
Yeah. So the product and the integral you can swap around because the integral completely the product completely factorizes. Sorry, the integral completely factorizes across all the terms depending on Z. So you can swap around. The integral goes inside, and then that Zi you can try to integrate out, right? Okay. And then you would obtain those marginalized likelihood terms. Mm-hmm. And then if you develop it further, you see that as a expectation under sampled data sampled from pi of x, the true one. Then what you are trying to do usually is to maximize this marginalized the likelihood, right? And then if you essentially there you add and subtract log of pi of x, and you obtain that KL.
So this is the final objective of gun learning in general?
Sorry, this is the final objective of the model I came up with. Okay. But now if I replace KL with Shannon, Jensen-Shannon divergence, I obtain the original GAN. If I change it with the F divergence, I obtain F GANs. Okay. If I replace it with Wasserstein, yeah.
Okay, thank you.
Yeah, thank you. This is just the references, just in case you're interested. So what I talked about at the beginning was the functional prior stuff. We did it also for Bayesian autoencoders because if you have an autoencoder is a model that has input and output, which is X, right? So it's a strange beast because there's no input, if you like. But what are good functions for the output? Well, these are the stuff that is sampled from P of X, and you have samples. So your samples become now what you're targeting with your functional prior, and it works really well. And then now we have this also thing about GANs that hopefully we'll go through some conferences soon, hopefully. Coffee break? No.
The last one said coffee break, yes.
Thank you for your great presentation. I have maybe a bit unrelated question, but you said that sometimes we need to factorize our distribution. For example, when we train a diffusion model, for example, for text, we usually factorize over tokens, right? Yeah, but maybe it is not natural way to do this. Maybe we should not factorize over that. Do you have any thoughts on that?
Okay, I think whenever you have any intuitions on things that should, they hold you back in your performance, you should try to do this. And perhaps what you're saying makes a lot of sense and would be worth trying. Before you try, you never know whether these things actually give you a big boost in performance or not. Maybe, sometimes even things that seem very sensible, implement them, and then it turns out that maybe they give you that very small improvement compared to the computational effort that you have to make to actually make it work. So try it out.
Okay. Thank you.
Thank you, guys.